Well, we've already spoken about kinetic energy and gravitational potential energy. There is one final form of mechanical energy, which is elastic potential energy. So let's go ahead and quickly sum up the details we need to know about that. So let's say I've got here a block that's sitting on the surface at some position x naught, and it's attached to a spring of spring constant k, and that spring is attached to a wall. And let's say right here, this is the spring's relaxed position, its normal equilibrium position. It's not stretched or compressed. And the question is, well, what happens when I pull the block and I have it now at this position x, so it's undergone a change in position of delta x? How has this changed the system? Well, I have basically now stored energy in the spring, because if you let go, the spring is going to pull back on this object and it's going to cause the object to gain kinetic energy. So there is potential energy present here, potential for motion. Okay, so what exactly do we need to do to figure that out? Well, we know that to calculate potential energy, a change in potential energy, this would be the work done against a conservative force. In this particular situation, the conservative force is the spring force. So that work is going to be the spring force times the distance we went against it, which was delta x. But what's the spring force equation? Well, that's just k delta x. In other words, that it's the spring constant multiplied how far we've stretched or compressed the spring. And unfortunately, that is not a constant value. And because it is not a constant value, we can't use this simplified form of the work equation anymore, because that force is going to change. So instead, we're going to have to figure this out from a force versus distance graph. So if we pull the spring some distance delta x, some spring force is being applied back to us, and it's going to increase as we pull and pull the spring. This is not a graph we are unfamiliar with. We've seen it quite a few times. Well, if we want to know the work at some point in this process, well, we're going to have to find the area underneath this graph. So let's go ahead and say, I'm going to look at this point delta x. I'm going to set x not equals to 0, so this would be right here delta x. And that would be the height of, this is a spring force at that point, and we want this area W. Well, that's the area of a triangle, so if I want to know that, that would be 1/2 base times height. Well, the base is delta x, and the height is the spring force. That would be 1/2 delta x times the spring force. I substitute in my equation for spring force, and I get 1/2 delta x times k delta x. You can multiply those delta x's together, and we end up with 1/2 k delta x squared. And this is actually the equation for the elastic potential energy, which we abbreviate US, of a system. So the elastic potential energy, which is often just colloquially called the spring potential energy, but elastic potential energy is a better term, is the energy stored when a spring is compressed or stretched. Because if you compress it, we've stored energy in the spring, so we must include the spring in the system. We've stored it in the spring, so when we let go, potential for movement. If I stretch the spring and I let go, potential for movement. So we must include that spring in the system. So delta US, that change in elastic potential energy in joules, is equal to 1/2 k delta x squared, where k is a spring constant. Remember, that's the units of newtons per meter, and delta x is the distance the spring has been stretched or compressed in meters. If we stretch or compress the spring more, the elastic potential energy of the system will go up. If we allow the spring to become more relaxed, so we allow it to go more towards its equilibrium position, well, then the elastic potential energy will in fact go down. Okay, that's the last type of mechanical energy we need to make sure we understand. That should be it.